Good evening, everybody. Can you all hear? Is it loud and clear? Perfect. We'll maybe start in another 2 minutes. Yeah. We'll give some time for the others also to join in. In 2 minutes, we'll start. Okay. So all you just need is just take about a sheet of paper or A4 sheet. That'll be good enough. Okay. Shall we start? Okay, no? So just before we start, what you call, you can get the tute. It's in the description. You can get it from there or the community. The link is put, the drive link is put, so you can get the tute from there. Okay, no? Perfect. Again, can you all of you all hear me loud and clear? Can all of you all hear loud and clear? Okay. Okay, right. So good evening, everybody. Welcome all of you all. So this is your final unit, unit 11. It's called matter and radiation. matter and radiation. Matter and radiation. So there is no significant connection to your other sections. So even the 2026 students can join in. There is no problem. They can join in and complete this final unit maybe a year ahead of the exam. Right. So today our main focus is, today I will give you a small structure. The main focus is to talk about black body radiation. Black body radiation. It's a very important part. Actually, in modern physics, a very significant development occurred at the analysis of black body radiation. Through the analysis of black body radiation. So we'll talk about black body radiation. Then we'll be talking about the photoelectric effect. Remember, Einstein won his first Nobel Prize for explaining the photoelectric effect. Photoelectric effect. Then we will talk about wave-particle duality. Wave-particle duality. De Broglie hypothesis. And if we have time today, we will talk about X-rays as well. So on Sunday, the significant part will be talking about radioactivity. We'll be talking about radioactivity, nuclear equations, nuclear reactions, and also particle physics. So those are the sections for Sunday. Today we'll be mainly focusing on these sections. We'll try as much as possible to plug this in here as well. Failing which, these three sections will be guaranteed done. Okay, no? So these are your overview: black body radiation, photoelectric effect, wave particle duality, X-rays. Okay, no? Right. Right. That's from this side. Okay. Right topic, all of you all. Black body radiation. Black body radiation. Black body radiation. Right. First of all, what is a black body? Remember, a black body is an object which can absorb all wavelengths of radiation. That's the definition. Huh? What is a black body? A black body is an object which can absorb all known wavelengths of radiation. Such a body is known as a black body. Okay, write the first note. A black body, please write first note. A black body is a body which can absorb all wavelengths of radiation. All wavelengths of radiation. All wavelengths of radiation. Right. So a black body can absorb. It's a perfect absorber. Short form you can remember. Perfect absorber. So black body is a perfect absorber. Remember this. Perfect absorbers are also perfect emitters. So if you absorb all wavelengths of radiation, you can emit all wavelengths of radiation as well. Next point, right. Perfect absorbers are also perfect emitters. Therefore, a black body will absorb all wavelengths of radiation. A black body will absorb all wavelengths of radiation and also emit all wavelengths of radiation. and also emit all wavelengths of radiation. And also emit all wavelengths of radiation. Okay, right. Now, practically, do we have an object like this? Yes. It's called the Lewis cube. It's called a Lewis cube. It is perfectly black, even from the outer surface. And there is a very small opening like this. A very small opening like this. So what happens is, when light enters here, or when light enters at any particular angle, reflection will happen inside continuously. Reflection will continuously happen inside until all the light is absorbed. No light escapes. There, no light escapes. So practically we have something called the Lewis cube. Yeah? The Lewis cube is an object which is known as a black body. So what is a black body? If a light radiation enters, it will completely reflect inside. No light escapes out. Always the light is inside. Okay? Always the light will remain inside. Such reflections will cause all wavelengths of light to be absorbed by this object. That's right. That's right. Practically, we have a cube known as the Lewis cube. We have a cube known as the Lewis cube. We have a cube known as the Lewis cube, which can absorb all wavelengths of radiation. Which can absorb all wavelengths of radiation. Which can absorb all wavelengths of radiation. Okay. Lewis cube is there, which can absorb all wavelengths of radiation. As indicated in the diagram below. As indicated in the diagram below. As indicated in the diagram below. Light enters the Lewis cube. Will reflect inside it and no light will escape. Will reflect inside it and no light will escape. Quickly draw this. Quickly draw this. Quickly draw. Right? Okay. Look at this carefully now. So perfect absorbers are there. They are called black bodies. They are called black bodies. Black bodies will absorb all wavelengths of radiation. Black bodies will absorb all wavelengths of radiation. Every black body is a perfect absorber, therefore it's a perfect emitter as well. Yeah. Perfect emitter as well. So therefore we can obtain this basic relationship. Okay. Therefore we can obtain this basic relationship. Okay. Right. Okay. Now, when we study this, there's a very important curve, Stefan-Boltzmann curve. We'll talk about the Stefan-Boltzmann curve later, but for now we'll focus on Stefan's equation or Stefan's law. Stefan's law, right? What does Stefan's law tell you? Look at this carefully. Let's say for a black body, should be a black body, yeah? Let's say for a black body, at a temperature, let's say T, at a temperature T, the rate of radiation energy emitted, per area, rate of radiation energy Q dot emitted per area is directly proportional to the fourth power of the absolute temperature of the object. What is this? Normally we draw the sun also like this, no? Imagine like the sun. Yeah. We assume the sun is also a black body. So let's say the black body has a temperature T. T is the temperature of the black body. Absolute temperature of the black body. Absolute temperature of black body. The rate of radiation energy emitted per area, Q dot divided by A. Q dot is normally considered as the rate of radiation energy emitted. So the rate of radiation energy emitted per area is directly proportional to the fourth power of the absolute temperature. Let's write it. Stefan's law. Let's write. Stefan's law states that the rate of radiation energy emitted by a black body, is directly proportional to the fourth power of the absolute temperature. The fourth power of the absolute temperature. The fourth power of the absolute temperature of the object. Fourth power of the absolute temperature of the object. Right now? I'll quickly draw this. Write it down. We can define Q dot, rate of radiation energy emitted. Rate of radiation energy emitted. Remember, it's in watt, joules per second. Joules per second means watt. A is the surface area of the object. Surface area of the object. Surface area of the object. Okay, no? Right. Quickly write down. Okay. Please write a bit quickly. So there's a black body. What's a black body? A black body is an object which absorbs all wavelengths. Also what? Emits all wavelengths. So black body has an absolute temperature T. It will emit all wavelengths of light. The rate of radiation energy emitted. So these watt, these area meter squared, watt per meter squared. So the rate of radiation energy emitted per area is directly proportional to the fourth power of the absolute temperature. So the unit symbols are T is absolute temperature of the object, A surface area of the object, Q dot T is rate of radiation energy emitted by the object. Okay, no? Clear? Perfect? Right. Okay. Very important, simple theory, yeah? Not difficult, very simple theory. Finished? Right, let's move on. So we can write here Q dot divided by A proportional to T to the power 4. Q dot divided by A is equal to, make this equation, sigma T to the power 4. Stefan's constant. Q dot is equal to A sigma T to the power 4. There you go. This is for a black body. For a black body, rate of radiation energy emitted is given by this particular equation. Write down below. Rate of radiation energy emitted is given by this body. So the value for sigma 5.67, normally 5.6. 10 to the power minus 8. If I look at this, watt per meter squared, Kelvin to the power minus 4. Watt per meter squared, Kelvin to the power minus 4. You call this the Stefan's constant. In reality, it's called Stefan-Boltzmann constant. Okay? This is the real thing. People just say Stefan's constant. Because in most books, it's written Stefan's constant. Stefan-Boltzmann constant. Okay? Stefan-Boltzmann constant. Okay? Right. Remember, this universe is made up of black bodies are ideal object. So many objects are non-black bodies. So many objects are what? Non-black bodies. So how do I modify this equation for a non-black body? How do I modify this equation for a non-black body? So what we do is, for a non-black body, we make this small modification. For a non-black body, we define something called the emissivity constant. Simply stands for emissivity. Emissivity of a surface. Simply. Emissivity of a surface, that's defined as the rate of radiation energy emitted per area by a non-black body divided by the rate of radiation energy emitted per area by a black body. This ratio is called your emissivity. Understood? So the rate of radiation energy emitted per area by a non-black body divided by the rate of radiation energy emitted per area by a black body. So what is a non-black body? A non-black body is a body which what? Does not absorb all wavelengths of light. All the other objects, if you see, now the room you are in now, the walls of the room, the cupboard, the windows, the table, all the desk, the books, they are all absorbing your radiation. But they will not absorb all wavelengths of radiation. Understood? So the objects in your room are what? Non-black bodies. Understood? They are non-black bodies. But Stefan's law is defined for a black body. So now we have to modify this for a non-black body. So emissivity equals rate of radiation energy emitted per area by a non-black body divided by rate of radiation energy emitted per area by a black body. So if I cross multiply this, we get the relationship. Q dot divided by A by a non-black body, that is equal to simple E times rate of radiation energy emitted by a black body. So I think now we have enough experience to write this. Q dot divided by A for a black body is sigma T to the power 4. Sigma T to the power 4, you can see, no? So here for a black body, we can directly write Q dot divided by A for a non-black body, that is simple E times sigma T to the power 4. Sigma T to the power 4. Okay, no? And we can modify it by one more step here. I'll write it here. Space, no? We can modify it there. Q dot is equal to EA sigma T to the power 4. This equation is valid for what? A non-black body. A non-black body. Non-black body will have an additional what? Simple E. Simple E is called what? Emissivity. Okay, no? Let's write. We can modify this equation. We can modify this equation for a non-black body. For a non-black body. We can modify this equation for a non-black body. Inside brackets, write. A non-black body will not absorb all wavelengths of radiation. A non-black body will not absorb all wavelengths of radiation. A non-black body will not absorb all wavelengths of radiation. Close brackets. Keep writing. We define the emissivity of a surface as indicated below. We define the emissivity of a surface as indicated below. We define the emissivity of a surface as indicated below. Okay, right. Carefully write down. So for a non-black body, emissivity, cross multiply Q dot A for a black body, Q dot A for a black body, sigma T to the power 4. Now we modify this and write cross multiply by A, EA sigma T to the power 4. EA sigma T to the power 4. This is a power, okay? This is a power. Right. Carefully write down. So you can answer in the chat. Is it clear so far? Any doubts, any questions? Is it clear? The last lesson means you should be very happy, no? Tell. Any doubts, any questions? No doubts, no questions. No doubts, okay, fine. Quickly write down. Is Bahasafir the youngest brother of the two Safirs, I thought? Huh? From St. Thomas College. I think so, I don't know. The name looks very familiar. Okay. There you go. So both brothers, I thought, both brothers, medical faculty. Right. Quickly write down. Okay, now? Now, the ones who are thinking will think and carefully ask, is this only emission? Isn't it absorbing? Yes, there is something called absorptivity as well. emissivity and absorptivity are equal for a particular wavelength. You know, particular wavelength at a given temperature. So fixed temperature, fixed wavelength, emissivity and absorptivity are same. You call this Kirchhoff's law as well. Not the one Kirchhoff's law in electricity, Kirchhoff's law in radiation. So I don't want to go in detail because there are so many other connected laws. So remember this very carefully. Here they talk about emissivity. There is also something called absorptivity. Why? Any object will absorb radiation as well as what? Emit radiation. When you are emitting radiation, you must use emissivity, simply. When you are absorbing radiation, you must use simple A, absorptivity. But Kirchhoff said for an object at a given temperature and wavelength, absorptivity and emissivity both are what? Equal. That means simple A and simple E both are what? Same. That bit I will write. Okay, no? So anything further means you are moving into much more deeper theory, which you will learn if you do physics in university. But for now, I'll just tell you that bit. Okay, no? Put a star and write. Put a star and write. Okay, let's write. When objects are emitting radiation, we use emissivity. Inside brackets simply. When objects are absorbing radiation, we use absorptivity. Inside brackets simple A. Put a star and write now. Okay, I will not tell it as Kirchhoff's law, but maybe I should say it as Kirchhoff's law, because most of you all won't learn it like that. You won't learn in detail. You just learn it to memorize. No, right? Anyway, put a star and write. Kirchhoff's law for radiation tells us that. Absorptivity and emissivity are equal. For a particular surface. At a given temperature and wavelength. Underline that. At a given temperature and wavelength. Okay, no? At a given temperature and wavelength. Right? So remember this absorptivity, emissivity, all these basic small concepts, because they can be very important when you solve problems. You know? They can be important when you solve problems. Right? Look at this carefully. Now, for example, let's take, you can consider as a special note. For example, let's take the sun in our constellation. The most brightest star we have is the sun. We can assume that the sun is a black body in your study in A levels. Temperature at the surface of the sun, I will take it as Ts. Temperature at the surface of the sun, I will take it as Ts. Sun's radiation is emitted in all directions. sun's radiation is emitted in all directions. Remember, the sun is a black body. I'll put short form BB. BB stands for black body. Yeah, easy no to remember. Right. Let's say the radius of the sun is RS. Radius of the sun is RS. Okay. First question or first idea that you have to think about is the sun is a black body. If the sun is a black body, that means it must radiate energy, it must give out energy, emit energy. How can I find the rate of this radiation emitted? Right? No? Very obvious question. So we know the sun is a black body, so we can use Stefan's equation directly. So rate of radiation energy Q dot from the sun. So Q dot from the sun means rate of radiation energy emitted by the sun. Remember, you have to be careful in unit 11. Whatever symbol you use, make sure you define it in your paper at least once. So when you are writing Stefan's equation, Q dot T equals sigma A T to the power 4, at least in the beginning, somewhere in the beginning of the question, you define what Q dot is, what A is, what sigma is, what T is it. So once you define these terms, then you can keep on working because you can use symbols. Loads are symbol-based questions. Okay. So Q dot is equal to area of the sun sigma Ts to the power 4. Sigma Ts to the power 4. We assume in our study the sun is a sphere. Sun is a sphere. So surface area of the sphere is 4 pi Rs squared sigma Ts to the power 4. This is the rate of radiation energy emitted by the sun. Okay, no? This is the rate of radiation energy emitted by the sun. So the sun is a black body. The sun is emitting radiation. The radiation energy emitted by the surface of the sun is given by this equation. Okay, no? Right. Now let's move on. Let's think a bit further. Roman 2. Now where are we? We are Earth. No? Not only the Earth. Everything in our solar system. We live in a constellation called the Milky Way. So here there are so many other stars, but here we will have what? The sun is the brightest star. So here Earth is somewhere here. I'll name it simple E, okay? Simple E. Sun will give out radiation energy. Now I'm assuming there is no other, there is no dust particles in the atmosphere. The Earth and the sun are directly facing each other. There is no atmosphere. Those things I have completely neglected in our study. Your A-level study is very basic and direct. It's concept based. Okay, you don't go into higher order, real life, real situation. Concept based. So the radiation from the sun will come towards the Earth. No? Radiation from the sun will come towards the Earth. Radiation from the sun will come towards the Earth. So if you look at this in detail, from the center of the sun, let's say the distance here is simple r. Simple r. Look at this carefully. Now, think and then tell me, will all the energy of the sun come to the Earth, or part or small part of the energy will come to the Earth? Now this energy is going in all directions. Will all this energy come to the Earth, or one part of that energy will come towards the Earth? Answer below. Will all the energy come, or just part of the energy will come? Quickly answer. All the energy or part of the energy? All the energy or part of the energy? Quickly. All the energy or part of the energy? So you're not answering now. Don't just look at it like watching a film. Huh? You need to ask questions. Part of the energy, very good. Part of the energy is going to be coming towards Earth, right? Okay. So what we define is, look at this. I will take a small part here, okay. from the sun towards where the earth is, the orbit radius is simple r. We are going to find out the amount of radiation energy passing through a unit per square meter here. So radiation is going through a big sphere. No? Earth is like this, a big sphere. I mean, the sun is like this, a big sphere is around it. All the energy is not going through a small part. A small amount of energy only will go through this 1 square meter. Understood? No? Right. So we will find this value. We call it a solar constant. We call it a solar constant. The rate of radiation energy of the sun passing through a unit area at a particular orbit. Passing through a unit area at a particular orbit. So here, Q dot from the sun divided by the area is this. All this energy is going through this big sphere. Big sphere. This 1 unit area is part of that big sphere. So I divide this total energy by the total area it's passing through. Total area is 4 pi simple r squared. That will give us the solar constant. That will give us the solar constant. So if I do substitute it here, solar constant is equal to Q dot we have found here, 4 pi rs squared sigma ts to the power 4 divided by 4 pi simple r squared. 4 pi simple r squared. From here we can say solar constant is 4 pi cancel off, rs divided by simple r whole thing squared, sigma ts to the power 4. There you go. Remember, this solar constant is something very important when they find out life. Now, if you take generally the solar constant, if it's between 4,000 to 6,000, that planet becomes a planet of what? Significance or research. You have so many planets that the NASA is finding whether there is life. How do they identify those planets? One idea is solar constant. If the solar constant is between 4,000 and 6,000, that gap, generally they take life can exist because the temperature conditions, the radiation conditions for microorganisms to exist is perfect. Now, if you take Earth, our solar constant is something like close to 5,000, 4,800 to 5,000. You know? So therefore, life will exist in that particular range. So one major parameter that they use to find out whether life can exist or not in a planet is the solar constant. If the solar constant, now if you take planets which are very closer, Venus and all very close, when they are very close, what happens is solar constant is too huge. Life can't exist. Then there are some planets very far away. When simple r is very large, the solar constant becomes very, very low. That is also useless. So there's a range, 4,000 to 6,000. That is a very significant period or significant value for the solar constant, which indicates life can what? Exist. Okay, no? Let's write. So this is a special note. Let's write. Consider the sun is a black body. Consider the sun is a black body. Consider the sun is a black body. Emitting radiation in all directions. 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 Roman number 1. Find the rate of radiation energy emitted by the sun. Find the rate of radiation energy emitted by the sun according to the diagram drawn. That means radius is given, temperature is given. According to the diagram drawn. Okay, keep about 2 lines. Roman 2. The Earth is orbiting at a distance simple r the Earth is orbiting at a distance simple r. The Earth is orbiting at a distance simple r from the sun. From the sun. Find the rate of radiation energy from the sun. Find the rate of radiation energy from the sun passing through a unit area through the surface of the Earth. The surface of these 1 meter squared are here, both same distance. Find the rate of radiation energy from the sun passing through a unit surface area of the Earth. Passing through a unit surface area of the Earth. This is known as the solar constant. This is known as the solar constant. This is known as the solar constant. Okay, now? Right, carefully draw it. Write it down. You are learning new things. New and very interesting things. Finished? Quickly write. Okay. Here, done now? Anybody who's still writing because they have to draw this also? Done. Finished. Right. Let's move on. Right. So remember, sun's radiation is coming as a black body. Earth is somewhere here. The amount of radiation passing through a unit area is, you must divide it by the big surface or big spherical area where the orbit radius is your radius. So I divide it by the big sphere, 4 pi r squared. From there I get the solar constant. Now look. Here, only one part is facing the sun. The other part is not facing the sun. No? There. One part is facing the sun. We can define this as the effective area. For example, if I have a ball here, if I hold the ball like this, that's the ball. So what is the area that you will see? If you are looking this way, what shape do you see? Somebody tell? If I'm holding a ball like this, what shape will you see? What shape will you see? What shape? Quick to tell. Circular, very good. That's called your effective area. Okay, if I hold the phone like this, what shape do you see? Tell me the shape, Pilu. What shape? This is circular. I mean the phone. Rectangle, very good. So remember, same way here, when the radiation is coming, effective area is being exposed. Effective area is being exposed. So we can say rate of radiation absorbed by Earth. Absorbed by Earth. Rate of radiation absorbed by Earth. Now we have solar constant. What is solar constant? Look. Amount of energy going through a unit area. So unit area of the Earth is this much. You look at the units, watt per meter squared. How do I find the area? Effective area. Effective area is exposed. So here you solar constant multiplied by the effective area. Effective area exposed to the sun or exposed to the radiation. So solar constant here we have found from earlier, Rs over simple r whole thing squared sigma Ts to the power 4. Effective area exposed is the effective area of the Earth. Pi Re squared. Remember this carefully. Radius of the Earth is Re. So the circle you see has a area pi Re squared. Pi Re squared. This is the rate of radiation energy absorbed by the Earth. Rate of radiation energy absorbed by the Earth. Clear? So here, again, if I hold this ball like this ball, if I hold this ball, you will see it as what? A circle. That circle is your effective area. Okay? That circle is your effective area. If I hold the phone, you will see a rectangle. You won't see a cube. You will see a rectangle. The rectangle is your effective area. So if this was the Earth, sun's radiation is coming and falling on this effective area. So solar constant, that means rate of energy going through a unit area, multiplied by the effective area, that's going to be what? The amount of radiation energy incident on the Earth. Now, just to make things simple, here we assume Earth is also a black body. Earth is also a black body. Otherwise, tell me, if Earth is not a black body, what should I do here? From your knowledge, tell me. If Earth is not a black body, what should I do? If Earth is not a black body, what should I do? You have learned, huh? You have learned from your knowledge, tell me. If Earth is not a black body, what should I do? Somebody tell. If Earth is not a black body, what should I do? Multiplied by simply, very good. But yeah, emissivity, or actually simple A, by absorbing, no, absorptivity. But emissivity and absorptivity both are what? Same. Whose law? Emissivity and absorptivity are same. Whose law? Whose law? You all learned it. Quickly tell. Whose law? Whose law? Kirchhoff's law of radiation. Clear? No? Right. Okay then. So we assume Earth is a black body. So directly we take, if the Earth is not a black body, if the Earth is not a black body, if the Earth is not a black body, rate of radiation energy absorbed simply Rs over simple R squared sigma Ts to the power 4 pi Re squared. Simple E equals simple A, whose law? Kirchhoff's law. Emissivity, absorptivity. Okay, no? Carefully write down. Carefully write down. So these are actually very simple. Huh? Very, very simple things. You can actually, practically these things are there. Now what happens is when you go to university, you learn so many other things also added to it. You learn physics in detail. So you have other objects also radiating, reflecting light. So those things also come into play. Okay, no? Write down. Okay. These emissivity and absorptivity. Emissivity, absorptivity. Okay, no? Right. So in the tute, we'll have problems. We'll meet this as we do questions. So for now, you understand the concept, how you absorb, objects absorb radiation and objects will not emit radiation. If it's a black body, they are perfect absorbers and also perfect emitters. Simple E equals simple A according to Kirchhoff's law. For a given wavelength at a particular temperature. Okay, no? Given wavelength at a particular temperature. Right. So this part, if it's a black body, this part additional if it's not a black body. Okay. Not a black body. So you need to understand that, I'll do a small summary of this. A concept that the object is a black body, it's giving out radiation, and there are other objects absorbing this. The absorbing object can also be a black body, no problem. Sometimes it's not a black body, then emissivity comes into play. If an object is emitting radiation, emissivity, absorbing, simply absorptivity, emissivity, absorptivity both are equal at a given temperature for a particular wavelength for a particular surface. Clear? So if I say emissivity or absorptivity, it's not two different things. It's the same thing. Okay? Like. Okay. Done? Anybody still writing this? Hopefully everybody is done. Okay? Right. Okay, good. So we'll move on. We'll move on. Again, something special. Remember, there's a reason why the special parts are given, because they are not significantly told, but they are there in the theory. If you take your radiation theory, these things are there and you should know. And they'll connect this. Normally this is your 10th essay question. 10 part A is thermal, 10 part B is matter and radiation. So there's a connection. Okay, no? So when you are doing this, you should know exactly what you are doing and then do it. It's a very simple concept, but important. Now, for example, look at this. Let's say there is a black body, temperature T. Temperature T. Look at this carefully. Yeah? I keep this black body inside a container, like a box. And the temperature of the box is, let's say, T1. Temperature of the box is T1. Okay, let me say this is T1, this is T2. Okay. So temperature of the black body is T1. Temperature of the container is T2. Okay. Now, if T1 is larger than T2, what will happen? The radiation emitted here, part of it is going to be absorbed by this container, no? Clear, no? Imagine now, why does the fish uncle put fish inside the ice box and put ice and come to keep the fish fresh, no? Otherwise it will what? The fish will quickly spoil. The blood will start oozing and it will spoil. Same way. So here you are keeping the black body inside a container, and here the object has a temperature T1, the surrounding has a temperature T2. So for me, the surrounding temperature is T2. It can be the atmosphere, it can be the box, or it can be the object and the box both together. Atmosphere and the box both together. Now you're standing here, your body is giving out radiation, the atmosphere is absorbing this radiation. Now what is your body temperature? 38 point. Bio students tell me 38.4. I think. Can't remember O-level work, 38.4 maybe. What is the atmospheric temperature? You tell me. What's the atmospheric temperature? 30 degrees, let's say, example. So your body temperature is much more greater than what? The atmospheric temperature. So radiation is emitted. This is what is seen in infrared cameras. You are giving out thermal radiation that can be absorbed by infrared cameras. Understood? Clear? 37. So you are giving out radiation. This can be absorbed by what? The surrounding radiation, surrounding environment. And that is only seen as infrared, IR. Okay, now? So here, the object is giving out radiation. Think carefully, huh? Also from the surrounding, radiation is coming into the object. Are you clear with this? Not only are we giving radiation, from the surrounding we are absorbing radiation as well. Is it clear? Understood? Anybody with a doubt here? We are giving out radiation. Also from the surrounding, we are absorbing radiation as well. Understood? Clear? Is it clear? Okay, now? So here if T1 is larger than T2, this black body is emitting radiation, also absorbing radiation. Net rate of radiation emitted by the black body. Net rate of radiation energy emitted by the black body. Oh, now wait. Emitted, no. So emission, let's take separately emission. Emission is A sigma T1 to the power 4. Absorption. The same object is absorbing, no. It's a black body A sigma T2 to the power 4. This difference. That is the net rate of radiation emitted. So net rate of radiation means emitted radiation minus absorbed radiation, that difference. From here you have A sigma T1 to the power 4 minus T2 to the power 4. Is it clear? Is it clear? Net means, now net, no. You are given a salary of 1,000 rupees. You take the 1,000 rupees and also you have taken a loan from the company. The company will deduct and give you 500. The loan is 500. 1,000 rupees given to you, 500 taken back. What's your net salary difference? Understood? Is it clear? Now clear? Net means the difference when you compare it with the environment. Right. So here, emitted, absorbed, net. There's a word we give for this. We call it the Prevost theory of exchange. Prevost theory of exchange. Prevost theory of exchange. That's right. Consider a black body of temperature T1. Consider a black body of temperature T1. Consider a black body of temperature T1. Where the surrounding temperature is T2. Where the surrounding temperature is T2. Surrounding temperature is T2. Keep writing. From the black body, there will be radiation emitted. From the black body, there will be radiation emitted. From the black body, there will be radiation emitted. And also it will absorb radiation from the surroundings. And also it will absorb radiation from the surroundings. And also it will absorb radiation from the surroundings. The net rate of radiation emitted by this black body, the net rate of radiation emitted by this black body is given by the following relationship. Is given by the following relationship. Okay, draw, write down. Okay, done. Okay, now, right? Perfect. Right. Okay. Now we come to a very important point. Now we spoke about Stefan's law. Only one law we spoke it. We spoke about the connection between black bodies and non-black bodies. We also connected this to a very simple example we see every day, which is what? The sun, yeah, which is the sun. So from the sun's radiation, how we calculate the solar constant, the rate of radiation emitted by the sun, and also the rate of energy absorbed by the earth, assuming the earth is a black body, and also if the earth is a non-black body. Okay, no? Right. Also we did, if object is emitting radiation, and also from the surrounding, if it's absorbing radiation, the net radiation absorbed or emitted can also be found. Okay, no? Right. Now, we move into a very important curve. We move into a very important curve. Generally, this wavelength curve is in nanometer. Okay. This is rate of radiation energy emitted per area per wavelength. Okay. Rate of radiation energy emitted, we call it intensity also. Per area per wavelength. To wavelength graph. To wavelength graph. Now this was drawn for a black body for different temperatures of the black body. And they observed or they saw a very significant connection. Yeah, they saw a very significant connection. Okay. So at a particular temperature, so this is a black body, yeah, for a black body, at a particular temperature, if you take the rate of energy emitted, it's not a constant fixed value. It's not a constant fixed value. It's like a curve. Where it's curve, it's increasing, reducing. For a particular wavelength, the rate of radiation energy emitted is maximum. The rate of radiation energy emitted is maximum for a particular temperature. Okay? For a particular temperature. And you can see that this covers a wide range of the wavelength. Covers a wide range of the wavelength. Okay? Covers a wide range of the wavelength. But the maximum rate of energy emitted occurs at a particular wavelength. For one particular wavelength, maximum radiation energy emitted is going to be what? There. Other wavelengths also radiation is there. But for one particular wavelength only maximum is there. Is it clear? Right. When you increase the temperature, you will see that the rate of radiation energy emitted at a particular wavelength will start to reduce. Okay? Will start to reduce. So we'll name this here. I think we'll name it here, no? Otherwise you can't draw the curve correctly. So peak is somewhere here. You know? And as the temperature increases, the wavelength will start to reduce. Maximum intensity, wavelength will start to reduce. So if you look at this, if I name it, T1 here, T2 here, T3 here, T4 here. T4 is larger than T3, larger than T2, larger than T1. There you go. This is a very important curve. It tells you that at different temperatures, there are different maximum intensities of or maximum rates of radiation emitted. It also tells you that when the temperature increases, the maximum rate of radiation energy emitted will start to reduce towards lower wavelengths. So the radiation peak will happen at lower wavelengths. Other radiations for other wavelengths also are there. But the maximum will start to be very specific, start to reduce. Also, if you look at it carefully, the area under each graph will also start to increase. So when the temperature increases, the area under the graph will also increase. Area under the graph will also increase. So you can see clearly there are some significant changes which happen in this particular graph. Yeah. Now, many people try to do this experiment. Many people tried doing it. But they actually could not come into a perfect conclusion of it. Okay. Perfect conclusion. Right. So you have two people called Rayleigh-Jean, then Planck's graph, Wien, there's a person called Wien. All of them did research. They tried to analyze this graph in detail, but they could not properly explain Wien came up with good solutions, which were very close to Max Planck's conclusions. Okay. So initially it was a Rayleigh-Jean curve. That's for history for y'all. No need to memorize them and anything. Historically, Rayleigh and Jean, they're the ones who drew this. Then Maxwell explained it, and then Wien explained it. So refined, the theory became a very interesting concept on black body radiation. Okay. So here, the rate of radiation energy emitted per area, energy per area is called intensity. So intensity per wavelength graph tells you that when temperature increases, the maximum value for the energy emitted or rate of energy emitted will be at a particular wavelength. And when temperature increases, this wavelength will start to reduce. Also, when temperature increases, the area under the graph will what? Increase. Area under the graph will increase. Okay, no? Okay. And if you look at this, if you draw a small sketch between the peaks, it will indicate that the peaks are reducing. The peaks are reducing. Okay, no? That's right. That's right. The intensity distribution of black body radiation, the intensity distribution, remember intensity, rate of radiation emitted per area. This is also called intensity. Yeah? This is also called intensity. So intensity distribution. Intensity distribution of a black body. Draw. Intensity distribution of a black body. Concentrate and work, please. Important. This is your last lesson. Final lesson. Okay. Quickly draw this. Okay. Okay. Let's write the significant points we learned from this. Put 1, 2, 3 and write significant points. Point number 1. Point number 1. Let's write. The black body radiation curve for a particular temperature. The black body radiation curve for a particular temperature has quite a complex shape for a particular, has a quite a complex shape. Has quite a complex shape. Distributed along a large wavelength. Distributed along a large wavelength. Distributed along a large wavelength. Point number 2. Point number 2. For every particular temperature, for every particular temperature, for every particular temperature, the maximum rate of radiation will be emitted. The maximum rate of radiation will be emitted for a specific wavelength. For a specific wavelength. For a specific wavelength. Right. Next point. When the temperature increases, when the temperature increases, when the temperature increases, the wavelength that the maximum radiation is emitted, the wavelength that the maximum radiation is emitted, the wavelength that the maximum radiation is emitted will reduce. Wavelength that the maximum radiation is emitted will reduce. Wavelength that the maximum radiation is emitted will reduce. Okay. Right. Next point. Now look at the board very carefully. These are simple things but important. So when the temperature increases for a particular wavelength, let's say this wavelength, it was here, no? Same wavelength, it becomes here. When the temperature increases, the radiation goes here. When the temperature becomes that, the radiation goes there. So for a particular wavelength, when the temperature increases, the rate of energy emitted will also what? Increase. Right there. For a particular wavelength, for a particular wavelength, for a particular wavelength, when the temperature increases, when the temperature increases, the rate of radiation energy emitted will also increase. The rate of radiation energy emitted will also increase. Rate of radiation energy emitted will also increase. For a particular wavelength, when the temperature increases, the rate of radiation energy emitted will also increase. Okay. Next one. When the temperature increases, the area under the graph will also increase. When the temperature increases, the area under the graph will also increase. When the temperature increases, the area under the graph will also increase. Okay. Right. Next is something very important. Black body radiation will never become zero. There is something called absolute zero, but for a particular temperature, black body radiation will never become zero. Okay, no? Put a star, right? At any given temperature, the black body radiation curves will never become zero. The black body radiation curves will never reach zero. Black body radiation curves will never reach zero. Okay, no? Right. Now, let's look at this in terms of theories. Huh? Let's look at this in terms of theories. So you all know all of this. You all are written it. I'll erase this a bit. Right. Look at this carefully. Now, what does the area under the graph give you? If I color this here, what does the area under the graph give you at a particular temperature? What does the area give? Okay. So the area under the graph, you multiply the y-axis to the x-axis. Rate of radiation energy emitted per area per wavelength multiplied by wavelength. So if I put units here, look at the board now. Q dot per area per lambda. Here lambda is there. So if you multiply Q dot per area per lambda multiply by lambda, lambda cancel off, Q dot over A. This is your area under the graph. Area under the graph. So what is Q dot over A? Rate of radiation energy emitted per area. Intensity. Yeah. Rate of radiation energy emitted per area, or in other words, intensity. So this will give you rate of radiation emitted per area. So some people short form call this intensity. Intensity of emitted radiation. That's your first point right there. The area under the graph, will give us the intensity of the emitted radiation. The intensity of the emitted radiation. Now, I think Imesha is asking a question. Why is the reason it can't reach zero? So you all know, no? Has absolute zero been reached? Has 0 Kelvin been reached? No. So what? Radiation is always there. It can't be zero, right? Simple things, try to connect it. You have learned these things in your science life. Now try to connect it. Right there. Show it. Area under the graph is the rate of radiation emitted or intensity of emitted light. So your axes, you can name it y-axis multiplied by x-axis. You have your answer. Okay. Have you all finished? Right. Next point. Next point. Look at this. When the temperature increases, the wavelength that the maximum radiation is emitted will start to reduce. We call this Wien's displacement law. Wien's displacement law. The wavelength that the maximum radiation is emitted. Lambda max, don't misunderstand. Lambda max is the wavelength, or lambda m is the wavelength that maximum radiation energy is emitted. Wavelength that maximum radiation energy is emitted. Maximum radiation energy is emitted. Right. So lambda m is inversely proportional to absolute temperature, right? When temperature increases, the wavelength that the maximum radiation energy is emitted will reduce, correct? When temperature is increasing, wavelength that the maximum radiation energy emitted will start to what? Reduce. Will start to reduce. So here, lambda m k times 1 over t, lambda mt is equal to k. This is called Wien's displacement constant. Wien's displacement constant, there is a value for it, 2.9 10 to the power minus 3 meter Kelvin. 2.9 10 to the power minus 3 meter Kelvin. Okay, no? Let's write. Let's write. Wien's displacement law. Wien's displacement law. Let's write. the rate of, sorry, the wavelength that maximum radiation energy is emitted, maximum radiation energy is emitted, wavelength that maximum radiation energy is inversely proportional to the absolute temperature. The absolute temperature. Write this carefully. Write this. Okay. Right? Okay, now? Right. What else can you learn? Now, there's a mathematical concept here which is actually connected to Stefan's law. They have found out that the area under a graph is proportional to fourth power of absolute temperature. So what's the area? Area is intensity, Q dot two over A. So therefore we can say Q dot two over A proportional to T to the power 4 means whose law? Stefan's law. From this curve they have found out. Okay, let's try next one. The area under the graph is directly proportional to the fourth power of the absolute temperature. The fourth power of the absolute temperature. Fourth power of the absolute temperature. Okay. Right. So once they started explaining this theory only, then Max Planck came in and said, right, this radiation emitted is actually not in what? Continuous. It's emitted in the form of packets of energy. So when this curve was drawn, for a particular temperature, the theoretical curve, this is a theoretical curve, no? Yeah. The theoretical curve and then Rayleigh-Jeans curve would slightly be different. Clear? Wien's displacement, you have only this one, nothing else. This is the only one you all have. Okay. So when they did experiments, they found out if you take Rayleigh-Jeans curve, I'll draw in a different color. For low temperatures, it never worked, but high temperatures, it came here. So like that, different people did a lot of experiments, and they couldn't get this into a particular, that means the theoretical curve and the experimental setup both should almost be same, no? From this, only they started developing concepts, and from there, Max Planck said, radiation energy emitted, looking at this, it's not fixed. You can look at the curve and say, for a particular temperature, it's not a fixed value. It's going on a complete range of values. Range of values means statistical application comes into play. That is why he said, radiation energy emitted is what? In the form of photons, packets of energy. You know? Put a sign, right? Constant values, sometimes they will give you. That's right. In classical physics, the Rayleigh-Jean law curve, the Rayleigh-Jean curve, Rayleigh-Jean curve would be correct for higher wavelengths, but would be wrong for lower wavelengths. At a particular temperature. Max Planck and Wien, who are developing the quantum theory, found out that their law would be correct for low wavelengths. But would be slightly wrong for higher wavelengths. And Planck's hypothesis gives us that. In black body radiation, energy is emitted. In the form of packets. Of energy known as photons. And light will be integer multiples of photons. Okay, no? So the biggest idea that came out of this is this concept of photons, which you all know. Photon energy is what? E is equal to h, right there. Energy of a photon, energy of a photon is given by the equation E equals hf. Energy of a photon is given by the equation E is equal to hf. H is Planck's constant, F is frequency. You can modify this. Travel at the speed c lambda. E is equal to h. F is c divided by lambda. This equation also is there. You can write down. E is equal to hf. Travels at the speed of light. Therefore, you can do the basic substitution. Okay, no? Right. Now, quickly, you learn a lot of work, no? Take your tubes. Take your tubes. You have 19 MCQs. Page 1 to page 6. 19 MCQs. Quickly do it. I will give you a very short time. You can maybe drink a glass of water and quickly work this out. I will be giving breaks. Quickly drink a glass of water. Quickly work out. Uh, Page 1 to page 6. Quickly work out. Then we discuss. Then we move on to photoelectric effect and wave particle duality. Okay. Quickly work. Right? People have finished. Right now, let's discuss MCQ number 1. MCQ number 1. A hot solid sphere is covered with a homocentric shell with a larger radius. If the space between the two spheres is a vacuum, the quantity of radiation absorbed by a small object kept inside the vacuum depends on. So look, here a hot solid sphere is covered with another sphere such that these in the center. In between these two, there is a vacuum. In between these two, there is a vacuum, right? The quantity of radiation absorbed by a smaller object kept inside the vacuum depends on A. Surface nature of the solid sphere and its area. So yes, because the rate of radiation energy emitted depends on the surface area and the nature of the surface. Statement A correct. Somebody is emitting energy, no? So the emitted energy depends on what? The surface area and the rate of radiation energy emitted. Right? Statement A is correct. Right? Next one, what? Part B, inner surface of the solid shell, right? From this shell also radiation is emitted, obvious. So inner surface area and its surface nature. B is also correct. B is also correct. So they're asking the energy absorbed by the what? Small object kept. Huh? Small object kept. So here, the energy absorbed by this object depends on the energy emitted by this object and the energy emitted by this object. So energy emitted by this object depends on the surface area and the surface nature. Energy emitted by this surface depends on the surface area and the rate of energy emitted. So A and B correct. Then what? Temperature of the solid sphere and its thermal conductivity. Temperature is correct. Thermal conductivity is wrong. Therefore, C is wrong. Only A and B is correct. Temperature, yes, that's accepted. Okay, now? Please don't engage in any other discussion because there are exam back students here. Exam back students here, please don't engage any other discussion. The chat is open. Only to talk about the work we are doing today. Please maintain minimum discipline here. Okay, now? Right. Question number 2. That is small sentence. That is small sentence. The energy absorbed by the small object. Energy absorbed by the small object energy absorbed by the small object depends on the energy emitted by the solid sphere, depends on the energy emitted by the solid sphere, energy emitted by the solid sphere. So you must remember, energy emitted by the solid sphere means Stefan's law. Q dot is A sigma T to the power 4. A is surface area. Depending on the nature of the surface means emissivity, simply. We don't know whether it's a black body or a non-black body. Surface nature comes. Clear, no? Depends on the energy emitted by the solid sphere and the energy emitted by the shell. And the energy emitted by the shell. Clear? Energy emitted by the shell. Right? It depends on the temperature of the object. It depends on the temperature of the objects. It depends on the temperature of the solid and the shell, solid sphere and the shell. It depends on the temperature of the solid sphere and the shell. But it doesn't depend on the thermal conductivity. But it doesn't depend on the thermal conductivity. Okay? Doesn't depend on the thermal conductivity. So only A and B is correct. Statement C is wrong. Right. MCQ number 2. MCQ number 2. Which of the following statements about thermal radiation is not correct? They are asking the statement which is not correct. Huh? First one. Thermal radiations are electromagnetic in nature. Correct? No? IR, infrared, electromagnetic. An object which absorbs radiation well is also a good emitter. Black body, yeah? Black body is a good absorber as well as a good emitter. Okay? Black body is a good absorber as well as emitter. So thermal radiation, we talk about black bodies, no, correct, no issue. Third one. Radiation loss occurs inside a thermoflask is minimized by applying silver on the walls. So when you apply silver on the walls, have you seen a thermos flask? At home you all have, no? Why inside is silver? Because the radiation will reflect and stay inside. Okay? They're saying radiation loss inside is minimized by applying silver on the glass walls. Correct. Third one also correct. Fourth one. Heat cannot be transmitted from one place to another by only radiation. Interesting question. Heat cannot be transmitted from one place to another by only radiation. There is sometimes only radiation happening. From the sun to the earth, only radiation. Okay. Fifth one. White clothes are recommended for warm places, while sunlight is because they do not observe radiation most. Correct? No? White clothes, cricketers and all, they wear white. Why? Less absorption, less black body, lesser the black body radiation absorbed. Darker the object, more what you call radiation absorbed. Lighter the clothes, less radiation absorbed. That's why they say don't wear dark t-shirts and walk on the road. It's actually very uncomfortable after some time. That's the reason. So fourth one is wrong. Huh? Right there. In a vacuum, heat radiation can be emitted. In a vacuum, heat can be transmitted only by radiation. Only by radiation. Right. MCQ 3. Figure shows the variation of intensity of radiation emitted with lambda. As the temperature of the black body increases, maximum intensity will. Temperature increases, maximum intensity will also what? Increase. But the wavelength will gradually reduce. So IM increases and the position of IM will shift to smaller wavelengths. Correct answer, answer 2. Third one, answer 2. Right. Moving on to the next one. What are they asking? What are they asking? Planck's constant, units of. That's easy, no? E is equal to HF. Joule, frequency per second. H is joule second. Fifth one. Sun radiates energy at a rate E per unit surface area. energy emitted per area, that is Q dot over A is E, okay? Don't forget. Assuming the sun is a black body, the surface temperature is Q dot A is T to the power 4. Therefore, E divided by sigma is T to the power 4. T is equal to E over sigma 1/4 to the power 1/4. That is given by the equation number 1, answer number 1. Answer number 1. Right? Okay. Yeah, so answer is found, answer 2. Question number 6. Here, fifth one, answer number 1. Question number 6. Figure shows the black body radiation curve of a body at a given temperature. Consider the following statements at a higher temperature. Higher temperature, lambda m will be lower. Correct? No, maximum wavelength will be lower. Intensity would be higher. Yes, area under the graph will be higher. Velocity of the emitted photons will be higher. Wrong. No? All radiation energy emitted is traveling at the speed of light, electromagnetic waves. So statement C is wrong. Huh? Only A and B is correct. Right there. All radiation energy emitted, all radiation energy emitted, all radiation energy emitted will be electromagnetic in nature. Will be electromagnetic in nature. Therefore, it will travel at the speed of light. Therefore, it will travel at the speed of light. Okay. It will travel at the speed of light. Okay. A and B correct. Answer 3. Seventh one, good question. What are they telling you? Seventh one. MCQ 7. Read carefully and do it. Two blocks A and B initially at 80 degrees Celsius and room temperature 30 respectively are hung from an insulated string in an evacuated chamber. Insulated string means what? There is no thermal conduction taking place. The energy is not going through the string, so only radiation is there, right? The enclosure is insulated from the outside, so no heat is coming from outside, no heat is escaped into the outside as well. Which of the following statement is correct prior to the system being reached equilibrium? So here there is a chamber. No heat is coming from outside. No heat is also going outside. Two objects are there connected to an insulated string. So no heat is going through the strings. No heat is coming from the strings, right? They are isolated. So A and B are initially at 80. Initially they are at 80. Room temperature is given as 30. Which of the following statements are correct? Which of the following statements are correct? Right. Let's look at the statements. Okay. Statement number 1, temperature of A and B and the enclosure remain unchanged. A, B and enclosure remain unchanged. Can't be, no. By thermal equilibrium has to take place. He has to give energy here. He has to give energy there. Energy will be transferred, so temperatures won't be constant. Why there's a high temperature here, there's a low temperature there. Room temperature is 30, no? So radiation will take place. This will emit energy there. This will emit energy there. From there, it will absorb some energy, and then all of them will retain much thermal equilibrium. Right. Statement 1 is wrong. Statement 2. Enclosure remains at room temperature, but the temperature of A and B will change. Temperature of the enclosure and block B increase, but that of block A will decrease. So, interesting. Fourth one. Temperatures of enclosure increases, but A and B remain unchanged. Can't be, no. The enclosure means environment temperature can't increase without these temperatures reducing. So this is wrong. Second one, enclosure remains at room temperature, but temperature of A and B will change. That is also wrong. If A and B are changing, heat is absorbed to the environment as well. Environment temperature also will change. Imagine you are going inside a bus, closed bus, or inside a classroom where the AC stops working. Imagine how uncomfortable it is. Ambient temperature will also what? Change. Okay, right. Temperature of the enclosure and block B increases, but that of A decreases. So they have, okay, fifth one, let's say we do. Temperature of A and B decrease, but the enclosure increases. So A is reducing means, can't you see there is transfer here? Then there is transfer there. Then there should be transfer this way. From A to B, from B to environment, environment to A. So there should be an equilibrium here. So these two can't be same. Why? Environment temperature will change, no? So only possible answer is answer number 3. When A temperature reduces, absorbing, B temperature increases, emission, this temperature also will increase, then all of them will what? Come to an equilibrium state later. Okay, that's right. That's right. Question number 7. The chamber is thermally insulated. The chamber is thermally insulated. So no heat can be lost out. No heat can be lost out. Right. Next. So read the question very carefully. They are given you blocks A and B initially at 80. Okay, right. If A emits energy to the environment, if A emits energy to the environment, if A emits energy to the environment, B will absorb the energy and the environment will absorb the energy. B will absorb the energy and the environment will absorb the energy. So the temperature of B and the environment will increase. Temperature of B and the environment will increase, while the temperature of A will reduce, right? No? They are telling this with a very specific reason. They are telling you last sentence there. Which of the following is correct before thermal equilibrium is reached, before equilibrium takes place? Imagine you, two of your friends or two friends is inside the room and somebody lights a fire to stay cold. Let's say you are cold, so you light a fire. What happens? You will also absorb heat. Your friend also will what? Absorb heat. Who is giving heat? Flame is giving heat. Imagine this was a vacuum. No heat is coming from outside. All the energy absorbed by the flame will be absorbed by you and your environment until or before the environment reaches thermal equilibrium. Clear? No? So what happens is when somebody emits energy, other two objects will what? Absorb the energy. Okay, right. Question number 8. Good question. If you see there, one is darkened. You put hot water, cold water. One is a normal cup. There you go. A, B, C, D are 4 cups of the same size. A, B are rough black surfaces. C, D are smooth, shiny surfaces. Smooth, shiny surfaces. Remember? Underline that, write a small sentence. In a smooth, shiny surface, radiation is absorbed at a very small rate. Radiation is absorbed at a very small rate. Right? Okay. So what are they saying? A is dark color. If you look at it, A is black color. you put cold water. Both are dark. What will happen? Black color, no? Good emitter. Radiation is quickly will emit. If radiation quickly emits, the temperature will quickly reduce. Here, cold water, what will happen? Here, temperature is less. Here, temperature is high. Here, rate of radiation energy emitted is more. Here, rate of radiation energy emitted is less. So, this will cool much more faster than that. That is for sure. Then what? So, A, B, C, D, shiny. Here hot, here also hot. Here shiny, less radiation emitted. Here dark, more radiation emitted. So hot water in a darker cup will reduce more than hot water in a shinier cup. Okay. Next, cold water here. Here what happens is, here it's going to absorb radiation from the surroundings. Absorb radiation from the surroundings, dark surface. Here less energy will be absorbed. Less energy will be absorbed. What can you say? Here more energy is absorbed, B will heat faster than D. Here more heat is emitted, A will cool faster than C. A will cool faster than C, B will heat faster than D. Correct answer is answer 1, right there. Right there. If we put hot water in a dark cup, if we put hot water in a dark cup, it will cool faster than in a shinier cup. It will cool faster than a shinier cup. So they are comparing hot to hot, cold to cold. Huh? Right. And if we put cold water in a dark cup, if we put cold water in a dark cup, if we put cold water in a dark cup, it will absorb more radiation than cold water in a shinier cup. It will absorb more radiation than cold water in a shinier cup. Cold water in a shinier cup. Right? Okay. Question number 9. Question number 9. A black body temperature T radiates 10 milliwatt. Q dot proportional to T to the power 4. 10 milliwatt T to the power 4, equation 1. If the temperature is double, what's the rate of radiation? Q dot 1. 2T to the power 4, equation 2. Divide the second equation by the first equation. Q dot 1 divided by Q. 2T to the power 4 is 16. So from here you have Q dot 1 is 16 times 10. How much? 160 milliwatt. 160 milliwatt. Correct, no? So whose law we are applying here? Stefan's law. No need to write the full equation. Just consider the variables. The variables are more than enough. Okay? The variables are more than enough. Right? So darker cups, darker shiny. Darker cups emit energy more, so it will cool faster. Also darker cups, shiny cup. Darker cups absorb more radiation than shinier cups, so it will heat more quickly. That is why I don't know whether you all have, if you all have a daralipa at home. I will have a daralipa, veragadapa at home. The bottom of the chatti is never clean. No? I mean, not inside the chatti. I mean, outside the clay chatti, we never clean it. No? You have anguru or soot, black color. Why? It'll heat more, absorb heat more quickly. Have you ever wondered now when they cook in daralipers, they don't clean the black charcoal at the bottom. Only inside the bowl, nicely washed with water. But below it, where the fire is lit or it touches the fire, we never, clean it. Why? That's because of black body radiation. Is it understood? Practical application in the kitchen. Understood? Is it clear? Okay, no? Right. Question number 10. Question number 10. Right. Question number 10. A star rotates about its own axis as shown. So star is rotating about its own axis. Star is rotating about its own axis. Now think about a bit of Doppler effect here as well. Huh? Which of the following graphs best represents the observation distribution intensity as a function of wavelength of a spectral line emitted by a certain gas in the star? When viewed from Earth, the broken line represents the expected intensity distribution of the spectral lines if the star does not rotate. Now, if the star doesn't rotate, no rotation, spectral line is given, intensity wavelength, IN lambda no. So dotted lines are given that. So we have a particular temperature, wavelength, you have maximum, right? Now what they are telling is, when the star spins, where will these spectral lines move into? Where will these spectral lines move into? Think about it carefully. When spinning, what is happening? What do you all think? So let's say you're on Earth, you're observing this. When this is spinning from one side and the other side, one side speed of light increases, while from the other side speed of light will reduce. Where do you learn this? When it's spinning, this way spinning means more speed. Speed of light plus the speed of the planet. Tangential speed of the planet. If I draw a top view here, this is the spin. Let's say the source is here, S. Let's say the observer is here on Earth. On Earth, observer. So here, what happens is, here there is a tangential speed plus the speed of light. Here, tangential speed is in that direction. Light is traveling in that direction. So the net speed here is C minus V. Here the net speed I can see is C plus V. So from one side, a higher velocity coming more quickly. Here going away. Here lesser velocity. Lesser velocity. Understood? So when the star is spinning, from one side, light is coming much more faster than the other side. Understood? From one side, light is coming much more faster than the other side. Faster the light comes, greater the frequency, greater the frequency like Doppler effect, higher frequency. That means what? Low wavelength. Okay? Low wavelength. Here, coming at a low velocity, that means what? It's coming slowly. Slowly means what? It's like removed. Frequency slightly less, wavelength is more. Okay, no? So that is the impact here. Now you must draw the curve correctly. But before that, let's write this slowly. When the star is spinning, light emitted from one side is observed at a higher velocity is observed at a higher velocity, therefore its frequency is much more higher. Therefore its frequency is much more higher. Therefore its frequency is much more higher. So this side higher frequency, frequency apparent much more higher. Therefore lambda apparent much more lower. Higher apparent frequency, lower apparent wavelength. Lower apparent wavelength. Okay. So lower apparent wavelength means now the wavelength becomes even lower. Even lower. Okay. From this side, speed is coming less. Speed is coming less means apparent frequency is less. Wavelength is large. Wavelength is large. Wavelength is large means it's somewhere here. So if this was star stationary star dotted line, rotating one is given by dark lines. So one side high frequency, low wavelength. On the other side, low frequency, higher wavelength. Or lesser apparent frequency, higher wavelength. So this curve is given by dotted lines. Curve is given by answer 1. Understood? Clear, no? Okay, no? So from one side, light is coming much more faster. Coming more quicker means apparent frequency is high, low wavelength. Here coming more slower. Slower means apparent wavelength is low means wavelength is large. Frequency low means wavelength is large. Okay, no? Right. Clear, no? Is it clear? Once you are doing the exam, is it clear? Understood? Is it clear? Yes or no? So this Doppler effect concept comes into play. Okay. So on one side, the velocity is much more higher, coming more quickly. Coming more quickly means apparent frequency is higher. Apparent frequency is higher means wavelength is lower. From the other side, apparent frequency will be slightly lower than this. So apparent wavelength will be larger than that. Okay, no? Right. Okay. Question number 11. Question number 11. Question number 11. If the absolute temperature of a body is double, the rate at which the radiation will be what? Double means 2 to the power 4. 16 times. Correct answer 5. Right. 12th one. Temperature of a sunspot is 4000 Kelvin, while surrounding solar surface is 6000 Kelvin. What's the intensity at the sunspot? Intensity at the sunspot is rate of energy emitted per area at the sunspot divided by rate of energy emitted per area on the surface. This is equal to sigma sunspot 4000 to the power 4 divided by surface sigma 6000 to the power 4. Sigma cancel off. 3030 2 over 3 to the power 4. 16 divided by 81. That's the ratio. 16 divided by 81, answer is answer 5. 16 divided by 81, answer is answer 5. Right? Okay. Question number 13. Question number 13. If the absolute value of the surface temperature of the sun was 3 times the existing value, the radiation of the sun would be mostly in what range? If the temperature now, normally what happens, they're telling, don't go in the hot sun, UV radiation is there. So imagine if the temperature of the sun now becomes triple the time, what happens? We'll have only UV radiation, nothing else. Answer is answer 5. Question number 14. Question number 14. Carefully look. Question number 14. two blades A and B, read the question carefully, two blades A and B. Two blades A and B fixed to a smooth axle as shown. You can see A front side is polished, back side is darkened. B front side is darkened, back side is polished. Two blades A and B on a smooth axle are kept inside an evacuated chamber. Evacuated means vacuum. So only radiation can be there. And lighted as shown in the figure. One side of each blade is polished, the other side is dark. Okay, right. So now what can you say here? The connection here they are asking is, blade A gets warmer than blade B. You can see on one side they are given light is coming from the left hand side. I don't know whether you are looking at this carefully. Light is coming from the left hand side. So you have one plate here, this is dark, this is bright. Dark means will absorb more radiation. More radiation energy absorbed. More radiation energy absorbed. Look at the other one, Vilu. Other one is B. Here dark, bright. Lesser energy is absorbed. Lesser energy is absorbed. Okay. Lesser energy is absorbed. Right. Now they're talking about a clock rotating. Interesting. Now rotating means momentum change should be there. No? Momentum change should be there. Okay. So what will most probably happen? So blade A will get more warmer. That's more radiation energy is absorbed. Blade A will be hotter than blade B. More radiation absorbed. Blade A is more hotter than blade B. Right. That is a fact. Okay. Right now. So here what? Here, what can you say? So rotation means like a momentum change. Somebody coming, knocking and reflecting. Knocking and reflecting. Bright means perfect absorbers, less radiators. Think carefully and answer. If you take this dark side, good absorbers, good emitters. Good absorbers, good emitters. Bright one, this one. Good absorbers, not good emitters. Good absorbers, not good emitters. Okay. So there you go. You have a small connection there. Interesting question. Interesting question. Huh? Right? Yeah. So they're saying, that's correct. So what can you say here? Brighter surfaces, less radiation absorbed. Darker surfaces, more radiation absorbed. So this is like photons coming in. Nah? These like photons coming in. Here photons coming in HF. Here. Photons coming in HF. Right. Now think and answer. So what can you say? Sorry. Right. So here what's happening is, here more absorption is taking place, just like cricketers playing in the sun. More absorption is taking place. Here, less absorption. So what happens is, light is coming and also rebounding. Some are bouncing back. Some are bouncing back means more momentum change here than there. Understood? Again, light is coming this way. Black surface is absorbing more light. A bright surface here is absorbing less light. Absorbing less means some are reflected. No, going in reflected means like a ball bouncing. Ball bouncing means more momentum change here than there. More momentum change than there means anti-clockwise rotation will take place. Understood? Is it clear? Okay, no? Right. So here, light is coming, knocking, and some are rebounding, big momentum change. Here, all the light is absorbed. Big momentum change here means what happens? Force is in that direction. Rotation will take place anti-clockwise. So what is your answer? What are they given there? So blade A gets warmer, accepted. Then blade B and rotates anti-clockwise. Correct answer is answer 2. Right now, white surfaces, photons will come and knock and rebound. Rebounding means momentum change is more. Right? That's right. On a dark surface, all radiation is absorbed. On a dark surface, all radiation energy is absorbed. On a dark surface, all radiation energy is absorbed. But on a brighter surface, less radiation energy is absorbed and also light is rebounding. And also light is rebounding. And also light is rebounding. So there is a bigger momentum change when it rebounds. There's a bigger momentum change when it rebounds, causing an anti-clockwise torque. Causing an anti-clockwise torque. Causing an anti-clockwise torque. Okay, now? Right. Question number 15. Question number 15. Total energy radiated by a black body is gathered for a minute and used to heat a certain amount of water. Okay, fine. Temperature of water got increased from 20 to 20.5. Good. If the absolute temperature of the black body is double and the above experiment is redone, the temperature of the water increases by, so you all know, Q dot is proportional to 4th power of absolute temperature, right? So rate of radiation energy emitted, heat given equal heat absorbed. So who is absorbing this heat? Certain amount of water, no? So here mass of water, specific heat capacity of water, change in temperature of water 20.5 minus 20 divided by time. Rate, no? T to the power 4. Equation number 1. Now what are they telling? If the absolute temperature of the black body is doubled, the temperature of water increases from 20 to how long? In the same time. So again, mass of water, specific heat capacity of water, theta minus 20 in the same time, double T2 to the power 4, equation number 2. So we are doubling it. Huh? So they want this temperature to divide second equation by the first equation. I'll just do it here. It's easier. Common terms cancel off. Theta minus 20 divided by 20.5 minus 20. Here 16. 2 to the power 4 is 16. No? So here theta minus 20. 16 times 0.5, that's 8 degrees. theta is equal to 28 degrees Celsius. Theta equals 28 degrees Celsius. Answer A. Okay, no? Right. Question number 16. Which of the following is not true regarding the rate in which body emits radiation? It's proportional to the surface area. It's proportional to the emissivity, correct? Proportional to emissivity of the surface of the body. It depends on the temperature of the surrounding. It does not depend on the thermal capacity of the body. So what are they asking you? They ask about the radiation energy emitted, no? Yeah. So here they are asking, which of the following is not true regarding the rate, that means the false statement, proportional to the surface area of the body. Yeah. Proportional to the fourth power of the absolute temperature. That's also correct. Proportional to the surface emissivity. Simply is there, non-black body. Huh? Non-black body. Next one. It depends on the temperature of the surrounding. Wrong. It depends on the temperature of the object. Fourth one is wrong. It does not depend on the thermal capacity of the body. Correct. Does not, no. Correct. The false statement is answer number 4. Right. Question number 17. A cylindrical copper block of radius r, length L. Cylindrical copper block. Radius r, length L means 2r. Radiates energy as a black body at temperature T. So here, what's the surface area? Q dot equals surface area. You have two surface areas, 2 pi r squared plus 2 pi r h 2r. Surface area sigma T to the power 4. Q dot equals 2 pi r squared plus 4 pi r squared sigma T to the power 4. Q dot equals 6 pi r squared sigma T to the power 4. Equation number 1, right? Then what? We are cutting this into small n disk of the same radius. Just like cutting a Swiss roll, we are cutting this into smaller parts. If you are cutting this into smaller parts, n number of parts. So each part is here. Same radius r, each part is 2r divided by n. Now for this we wrote, for that you must write Q dot equals 2 pi r squared, 2 pi r h is 2r over n. Total surface area n number of, like this there are n number, sigma T to the power 4. Simplify it carefully. Here Q dot 2, I'll name this Q dot 1. Q dot 2, 2 pi r squared plus 4 pi r squared over n times n sigma T to the power 4, equation 2. Here equation 1. So this I have taken for the complete Swiss roll. This I have taken for n number of slices of the Swiss roll. I'll assume it's a Swiss roll. The same cylinder. So from one cylinder, total surface area is 2 circles, 1 circular surface. 2 circles, 1 circular surface times n. This is for one surface area. You have n number of times like that. Okay. They're asking the rate of emission of radiation will increase by a factor. Okay, interesting. Increase by a factor. Simplify this a bit further. Q dot 2 divided by Q dot 1. Here you will have, let's multiply 2 pi r squared 4 pi r squared over n times n sigma t to the power 4 divided by 6 pi r squared sigma t to the power 4. Be careful when you solve this. Sigma t to the power 4, sigma t to the power 4 cancel off. Okay. Here common terms take it out. 2 pi r squared take it out. 1 plus 2 over n times n divided by 6 pi r squared. Here times 1 times 3, 1 over 3, open brackets, n plus 2. N plus n cancel off 2. So your answer is n plus 2 divided by 3. N plus 2 divided by 3. There you go. Is it clear? So from one large, here large cylinder, rate of radiation energy emitted is given. Here n number of small cylinders, rate of radiation energy emitted. Divide one by the other, you have your factor. Divide one by the other, you have your factor. Clear? Right. Okay. Question number 18. When a body temperature of a person is 35 Celsius, peak wavelength emitted is 9.4. So Wien's displacement law. If his body temperature increases to 39, now when you're sick, your mother will catch and say, my God, the body temperature, that's what wavelength of radiation emitted is high. The wavelength changes. Higher temperature means lower wavelength. That's how you start feeling it. You know, when you're having fever, you put your hand underneath and check. Same way. So here, question 18, lambda m times t is going to be constant. So here 9.4 micrometer, temperature must be in Kelvin. 35 times 273, add it. 308 Kelvin, that is equal to K. Again, temperature is 39, what's the wavelength? 39 means you add 4 here, 312, same K. Both equations are equal, so just you can say 9.4 times 308 equals lambda m times 312. So maximum wavelength emitted is 9.4 divided by, into 308 divided by 312 micrometer. No? So if you simplify this, can I divide it? Yes, no? If I divide this by how much? 4 times 7, 28. Again 28, 7. 4 times 7, 28, 32, 8. 77 over 78. Correct answer is answer 3. Right. Last one, MCQ 19. A person with a surface body temperature of 30 degrees Celsius is in an environment of temperature 20 degrees Celsius. The net rate of heat loss, right? No? Net rate of heat emitted to environment. Remember, you're emitting to the environment and absorbing also from the environment. A sigma 303 to the power 4 minus 293 to the power 4. So net rate of heat emitted is proportional to 303 to the power 4 minus 293 to the power 4. Correct answer is answer number 1. Correct answer is answer number 1. Okay, now. So we have done the section, completely discussed all the MCQs up to given so far. Right. Okay. Now you all should have your own water break and food break and tea break. Won't give separately. Right, no? Okay. Right. Then we move on to photoelectric effect. Photoelectric effect. Right. Our main target is photoelectric effect and wave particle duality. If we have time, we'll do X-rays. I think we'll have time for these two, photoelectric effect and wave particle duality. So X-ray will be doing on Sunday. X-ray, radioactivity, nuclear equations, and particle physics. Okay, right. So what is photoelectric effect? Look at this. If there is a metal surface, and if light radiation falls on this, they observe sometimes electrons are emitted. Okay? So what is happening? When on a metal surface, when light radiation falls on the metal surface, under certain conditions, electrons are emitted. Now look at this. Under certain conditions, electrons are emitted means these are called photoelectrons. Photoelectrons. It doesn't happen all the time also. Only if the radiation is beyond a certain frequency. Now, people could not explain this for decades and decades. So, 1905. In 1905, Einstein won his first Nobel Prize for explaining this photoelectric effect. Okay? For explaining this photoelectric effect. First, he explained it. Then other people did practicals and then found it to be true. Okay, no? So these are what Einstein said. Einstein said, if we think light is continuous, we can't do this. If we think light is continuous like a river, we can't do this. He said, Maxwell had said about photons. He said, light is not continuous, but light is like what Maxwell said, photons, discrete packets of energy. So this is how Einstein was thinking. He said, one photon means one packet of energy is coming in. One packet of energy is coming in. Imagine like a ball. One packet of energy is coming. This packet of energy, the moment it hits the metal surface, instantaneously, one electron inside will absorb this energy. One photon, one electron. This is how Einstein explained this. Photon is bringing energy. One photon comes and knocks on the metal surface. Instantaneously, electron will absorb this. It will do some work to come to the surface. We call it work function. That's the symbol. And if it has excess energy, it will come out with a maximum velocity. If it has excess energy, it will come out with what? Maximum kinetic energy or maximum velocity. So look at this carefully. When light radiation falls on a metal surface, one photon is completely absorbed by one electron. One photon is completely absorbed by one electron. This electron will do some work to come to the surface. If it has excess energy, it will come out with a maximum velocity. Einstein actually wrote law of conservation of energy. He said, energy given equal energy absorbed, energy emitted. So whatever energy is given is absorbed by the electron. Energy given is HF. Electron will absorb all of this energy. It will do work to come to the surface. That's called work function. Any excess energy, it will have a maximum kinetic energy. Phi is called work function. Work function of the metal. Remember, from metal to metal, it will change. So the work done to move from to the surface by the electron, that's called work function. Remember, work function is connected to HF naught. F naught is called threshold frequency. Threshold frequency. Threshold frequency. Threshold frequency depends on the metal. Depends on the metal. Different metals will have different threshold frequencies. So this is Einstein's equation. Einstein's equation for photoelectric effect. And he found out that the work function equals HF naught. Where F naught is threshold frequency, from metal to metal, F naught will what? Change. Understood? Now if I substitute it here, we can get a modified equation, HF equals HF naught plus KE max. HF naught plus KE max. There you go. Einstein's photoelectric effect equation. This section you'll be using this equation to solve problems. For now, let's write this down. Let's write photoelectric effect. It was observed that when light radiation falls on a metal surface, when light radiation falls on a metal surface, when light radiation falls on a metal surface, at certain instances, photoelectrons are emitted. At certain instances, photoelectrons are emitted. At certain instances, photoelectrons are emitted. Photoelectrons are emitted. Full stop. Einstein explained this in the following manner. Einstein explained this in the following manner. Einstein explained this in the following manner. That's right. That's right. Light travels in discrete packets of energy called photons. Light travels in discrete packets of energy called photons. Lights travel in discrete packets of energy called photons. In discrete packets of energy called photons. When one photon, first next point, next line, right? When one photon is incident on the metal surface, when one photon is incident on the metal surface, when one photon is incident on the metal surface, instantaneously all its energy is absorbed by the electron. 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 It will do some work to move to the surface of the metal. It will do some work to move to the surface of the metal. It will do some work to move to the surface of the metal. Inside brackets, write work function. Inside brackets, write work function. Work function. And if it has excess energy, and if it has excess energy, and if it has excess energy, it will move out of the surface with a maximum kinetic energy. It will move out of the surface with a maximum kinetic energy. It will move out of the surface with a maximum kinetic energy. Right. Keep writing. Keep writing. Next point. The work function will change from metal to metal. The work function will change from metal to metal. Work function will change from metal to metal. Because the threshold frequency will change from metal to metal. Because the threshold frequency will change from metal to metal. Threshold frequency will change from metal to metal. Write this down quickly. It's a very simple theory. Yeah? Finished? Have you all finished? Okay, now? Right. So we can write modifications for this. HF equals phi plus KE max. HF equals HF naught plus KE max. Look at this carefully. Make KE max the subject. HF minus HF naught. Remember, kinetic energy can't be negative. F minus F naught. So what can we observe from this? First situation. If F is larger than F naught, incident frequency, F is incident frequency greater than threshold frequency. Incident frequency greater than threshold frequency. If you go back, I have drawn and shown here. Incident frequency here. Photon is coming with a frequency F. Incident frequency, right? So if F is larger than F naught, KE max is greater than 0. Correct, no? If this is larger than that, this is a positive answer. So what? KE max is larger than 0. Photoelectrons exist. Photoelectrons exist. What is your second observation? If F is equal to F naught, incident frequency equals threshold frequency. If these two are equal, they will cancel off and become 0. KE max is 0. What do you mean by KE max is 0? That means the electrons will come to the surface, but no excess energy, so it will remain at the surface, won't come out. No photoelectrons emitted. No photoelectrons emitted. So Einstein was able to explain why sometimes it's emitting, sometimes it's not emitting. Also next case, third one. What if F is less than F naught? F is less than F naught means negative answer. Maximum kinetic energy is always positive. You can't be negative. Therefore, what? No photoelectrons emitted. No photoelectrons emitted. So Einstein was able to explain why sometimes photoelectrons are coming out, sometimes photoelectrons are not coming out. That was his whole job. That's why he won the photoelectric effect Nobel Prize. So Nobel Prize should be a significant. Now remember, sometimes you all might think Nobel Prize means what? Even though the work might be very small, but if it's actually uh, drastically changing the course of the universe or course of science, those people are what given the Nobel Prize. So Nobel Prize is not given for everybody. Everybody does research, but whatever they find out, if they changes the course of science, changes the path of science, those are the ones that get Nobel Prize winning research. Is it clear? So Nobel Prize winners are generally what? A very rare breed, uh, being specifically because what? Whatever they develop will alter the course of nature, will alter, change it. This concept of photons came into play, application is there, so many other applications are connected to photoelectric effect. Huh? When satellites are going up, you are having solar cells now, all of that is connected to what? Photoelectric effect. It altered the course of science. Okay, now let's write this down. The Einstein's observation can be summarized as indicated below. Can be summarized as indicated below. Quickly write down. Okay, finished. Right. Okay. Keep writing this. HF equal HF naught KE max. Remember, photons travel at the speed of light. So you can put C over lambda naught. KE max is half mass of electrons, velocity of electrons squared, V max squared. Lambda naught is called threshold wavelength. Threshold wavelength. Threshold wavelength of the metal. Of the metal. Lambda, incident wavelength of radiation. Write this also. Incident wavelength of radiation. Now just a bit more. I mean, you know the equations now. Now it's just to prove later how Einstein's theory was proved by other people. Right? Okay. Right now? Okay. So in calculation, we'll be using this equation, doing the substitution, getting your relationships. Okay, right. Now later they proved whatever that Einstein said in terms of graphs. These graphs are important. They'll ask for MCQs, they can ask for what? Essay questions as well. Look at the board carefully. So what they did was they had an evacuated chamber. Right? Evacuated chamber, vacuum chamber. Here you have an anode. Here you have a cathode. Cathode metal is there. This is connected to, here there is a voltmeter connected here. Here a microammeter connected there. Microammeter connected there. And here we have an anode. Here we have an anode. So variable resistor like this, we can change the resistance. Okay. We can change the basic resistance. Connected like this. Okay, now we can change the resistance there, right? Now look at this carefully. Look at this carefully. Okay. What's happening here is light radiation is incident on this metal here, cathode. Electron is emitted, it will come and collide with the anode. Electrons are coming and completing here. So one photon, one electron. Two photons, two electrons. Clear? So the number of electrons depends on the number of photons. One photon, one electron. Two photons, two electrons. So the number of electrons means the current depends on the number of photons coming in. Clear? So number of photons, number of incident photons directly proportional to number of photoelectrons. Number of photoelectrons. Therefore, we can say number of incident photons means intensity. Intensity of light proportional to number of photoelectrons. Number of photoelectrons. So one photon, one electron. So electron coming here means it's like current going in the opposite direction. So there will be a reading here. That is your photocurrent. Understood? So later people develop this practical and they put one photon, one electron comes out. You can find the current. Actually, once you know the current, you can find the number of electrons. No? How? Q is equal to IT. Total charge is multiples of electron, n times E. So number of electrons per unit time you can find. Okay, now draw this quickly. Draw this. To make sure electrons go correctly, you can curve this and draw. Best this curve and draw. Just make it curve. So it will be focused there. No? Right. Let's write here. First observation. When light radiation is incident on the cathode, when light radiation is incident on the cathode, photoelectrons will be emitted. Photoelectrons will be emitted. Photoelectrons will be emitted. Photoelectrons will be emitted. And these electrons will come towards the positive anode. These electrons will come towards the positive anode. These electrons will come towards the positive anode. And we can read its current. And we can read its current. We can read its current. Which is known as the photocurrent. Which is known as the photocurrent. Okay. Which is known as the photocurrent. Clear? Okay. These are your changes, observations. First one. One photon will emit one electron. One photon will emit one electron. One photon will emit one electron. Come on. And when the number of photons increase, when the number of photons increase, when the number of photons increase, the number of electrons will also increase. The number of electrons will also increase. The number of electrons will also increase. Therefore, the photocurrent will increase. Therefore, the photocurrent will increase. Now, write this. Number of incident photons proportion number of photoelectrons. Number of incident photons means intensity of light. Intensity increases, number of photoelectrons will also increase. Number of photoelectrons will also increase. Okay, no? Right. Okay, look at this graph. Now, voltage current graph, photocurrent. We can change this voltage by changing the resistance here. Okay. What they found out was, if the intensity is constant, intensity of light constant. If intensity of light is constant, that means number of photons coming is constant. The photocurrent is constant. Even if you change the voltage, bottom voltage, number of electrons emitted will not change, correct? One photon, one electron. Number of photon constant means number of electrons coming out constant. Number of electrons coming out constant means current is constant. Doesn't depend on the voltage. Right? That's right. If the intensity is constant, if the intensity is constant, if the intensity is constant, the photocurrent will also be constant. The photocurrent will also be constant. And it doesn't depend on the voltage applied. And it doesn't depend on the voltage applied between the anode and the cathode. Doesn't depend on the voltage applied between the anode and the cathode. Doesn't depend on the voltage applied between the anode and the cathode. Okay, quickly draw. Quickly draw. Finished. Done. Okay. Now this is intensity. Intensity, I'll take it as I1. Current is I. Remember, when the intensity is double, the current will also double. Intensity 2I1, current is 2I. So when intensity is double, current will also double. Intensity is triple, current will also what? Triple. Intensity is half, current will also become half. I1 divided by 2, here current will also become half. Right there. The current depends on the intensity. The current depends on the intensity. The photocurrent depends on the intensity. It doesn't depend on the external voltage supply. It doesn't depend on the external voltage supply. It depends on the supply. Doesn't depend on the external voltage supply. When the current increases, it means that the intensity of light is also increasing. It means that the intensity of light is also increasing. It means that the intensity of light is also increasing. Right? Quickly draw this second diagram now. First one done, now second done. New one draw it. New one draw it. Right? Okay. Now look at this. I'm going to erase this picture. Not picture, this. Because there is some more points to tell. Right. Now you can see here, if I write HF equals HF naught plus KE max. electrons have a maximum kinetic energy. So what they did was they tried to stop the electrons. Now, how do you stop the electrons? Think at that. Light is falling on the cathode, electrons are coming out. That means HF is larger than HF naught. So now electrons have come to the metal surface. They are trying to come out with the remaining energy, HF minus HF naught. When they are trying to come out, how can I stop it from coming? To stop it from coming, this is what you should do. You must change the terminals here. Change the terminals and the resistance here. There you go. Connect opposite. Make this negative, make this positive. And you keep changing the resistance until you reach a particular voltage called stopping voltage. The voltmeter reading here will read stopping voltage when this electron stop moving out. When the electrons stop moving out, no electrons are coming out. By negative, electron is negative, here negative, no. Electron is negative, here also negative. Electron is negative, here also negative. Negative, negative, repulsive. So I apply an external energy, to keep the electron inside. In other words, look at the board. In other words, photon is incident, electron has done work, come to the surface, but it can't come out. Why? I'm doing and giving a energy externally to stop it from coming. The external energy given must be equal to the kinetic energy. So Ke max, remember I'm making an electric field. We are making an electric field to stop this. So the work done on the electron is EVS. We have done this under electric fields. So electrons are coming out. I'm going to stop it. I want to stop the Ke max. So I must do energy EVS. Charge of electron into potential difference. Charge W is equal to V times Q. Delta V times Q. Is it the work done? I must do an external work done to stop the kinetic energy equal to the kinetic energy. So therefore HF equals HF naught. I can put EVS. VS is called stopping voltage. VS is called stopping voltage. Okay. No need to draw this full thing. But this thing you must draw right here. If we can apply an external energy, equal to the kinetic energy, using an electric field, we can stop the electrons from moving out. We can stop the electrons from moving out. And this voltage is known as the stopping voltage. And the voltage between the anode and the cathode is known as the stopping voltage. The voltage between the anode and the cathode, stopping the electron from coming out, is known as the stopping voltage. The voltage between the anode and the cathode, stopping the electron coming out, is known as the stopping voltage. So electrons are trying to come out. I'm applying an external energy equal to the kinetic energy to stop it from coming. So wherever there is Ke max, I can put EVS. PS is called stopping voltage. Write down. HF equals HF naught plus EVS. Another modification. Another modification. Another modification. Right? So light is falling, electrons are coming out. The moment it comes on, I'm pushing it back in. I'm applying an energy and pushing it back in. That external energy should be equal to KE max. So EVS is your energy. HF equal HF naught plus EVS. HF equal HF naught plus EVS. Right now? HF equal HF naught plus EVS. Right. Okay. I hope you wrote this. Right. Now look at this. I'll erase this. Now look. Now incident frequency constant. Intensity constant. Intensity constant. On a metal. So on one metal means what? Threshold frequency. So current will travel. Stopping voltage is a reverse voltage. We are turning the terminals. Somewhere it will come and stop. That's called your stopping voltage on a metal. Look at the board. Look at the board now. Simple, simple. Tell me now. What if you have different incident frequencies? Simple F is incident frequency. F1 larger than F2 larger than F3. Single metal, one metal. Intensity constant. Intensity constant. Right. Now, what are things that you know? Does the current depend on the incident frequency? Remember, all these are greater than threshold. F naught is threshold frequency. F naught is threshold frequency. It should be greater, no? Threshold frequency. Less than the threshold means nothing will happen. So, one photon, one electron. There you go. Intensity is constant means constant current. Whatever the incident frequency, see, F will change, your energy will change. But number of electrons coming out only depends on the current. Current depends on number of electrons. Number of electrons depends on the intensity. Right. What about the stopping voltage? Now think. HF minus HF naught equals EVS. Divide by E. H over E is F minus F naught, that is Vs, stopping voltage. What can you say? F is larger than F naught means when F is larger than F naught, greater difference, greater stopping potential. So F1 has the biggest difference. So F1 will have the biggest stopping voltage. F2 is smaller than this. F2 minus F naught is even lesser. F2 is here. F3 is slightly larger. So F3 will have a smaller stopping voltage. F3 will have a smaller stopping voltage. Clear? F3 will have a smaller stopping voltage. So here, incident frequency constant, intensity constant, stopping voltage there. Here, different incident frequencies, single metal, single threshold frequency, intensity constant means current constant. But stopping voltage will change depending on the frequencies. Larger incident frequency means larger stopping voltage. Smaller stopping incident frequency means smaller stopping voltage. Right. Okay. Draw. Draw. Let's write. When the incident frequency changes, when the incident frequency changes, the stopping voltage will also change. The stopping voltage will also change. Stopping voltage will also change. Stopping voltage will also change. Ah, one more graph we can edit. One more graph we can edit here. I think. Look at this. Single metal, one metal, different intensities. Different intensity, constant frequency, incident frequency. Different intensities means different currents. Different intensities means different currents. But intensity has no relationship to the stopping voltage. Incident frequency should be constant, single metal, single threshold frequency. So everybody will come and stop at the same location. Same stopping voltage. Clear no? Single metal, different intensities, constant F. Constant F. Intensities are different. Here intensity I, 2I, 3I. Different intensities, different currents. But stopping voltage is same. Because stopping voltage doesn't depend on intensity. Draw, draw, draw. So these are very important in your graphs. Huh? Very important basic graphs. Is it clear now? So photo current depends on intensity. Right now? Kinetic energy depends on incident frequency and threshold frequency, right? If I can stop the electrons coming out by applying an external voltage, that voltage is called stopping voltage, right? So I modify and I get this equation. Constant frequency, intensity constant, constant current, stopping voltage will stop. Constant intensity, different incident frequencies. Larger difference, larger stopping voltage. Smaller difference, smaller stopping voltage. Next. Different intensities, currents are different. Single metal, stopping voltage is same. That means F and F naught will be same. No? Single intensity, single metal, F minus F naught same. Stopping voltage same. Right. Is it clear? Remember, Einstein did all of this without this practical. Huh? Others only did the practical and said Einstein is correct. What Einstein did was took a piece of paper, looked outside, thought and wrote. That's it. That is what theoretical physicists do. Theoretical physicists, they formulate things. Then you come the, what you call, experimental physicists. They are the ones who do the practical and they prove it's correct. Okay. Technically, experimental physicists get more funding, more money. What you call, theoretical physicists are, they are in their own world. No? They sit and they think and they formulate. You know? Right. Quickly draw, quickly draw. Right, done. Okay. Also now we can draw two graphs. HF equal HF naught plus KE max. KE max equals HF minus HF naught. Graph is of the form y is equal to mx minus c. That means here incident frequency, maximum kinetic energy for metal number 1, I can draw this. From metal to metal, F naught will change, y intercept will change, but the gradient is constant. Gradient is constant. So different metal, y intercept will change. Gradient is constant means they are parallel lines. Here metal number 2, here metal number 3. All these are parallel to each other. Different metals, different y intercepts. But all the gradients are same, so they are parallel to each other. Parallel to each other. What can you say about the x-intercept? X-intercept means y value is 0, kinetic energy is 0. So kinetic energy 0 means HF minus HF naught equals 0, F equal F naught. Here only you have the threshold frequency. Your x-intercept is your threshold frequency. X-intercept, threshold frequency. Threshold frequency. That means from metal to metal, threshold frequency will change. Here metal number 1 here, metal number 2, metal number 3. Also there's another graph you can draw. HF equal HF naught plus EVS. Wherever there is kinetic energy, you can substitute this, E charge of electron. Simplify this, EVS equals HF minus HF naught, Vs equals H over EF minus H over EF naught. Graph is of the form y is equal to mx minus c. What do you learn from this all? H over E is constant, but F naught will keep on changing. So your graph is going to be very similar to this. Incident frequency, stopping voltage. Incident frequency, stopping voltage. Different metals will be parallel to each other. Same as this. Metal 1, metal 2, metal 3. All are parallel. All are parallel. Why? Because H over E is same. But y-intercept will be different. What about the x-intercept? X-intercept will give you threshold frequency F naught like here. Why? This part is 0, no, this part is 0 means F equal F naught, threshold frequency. Draw. Draw. So experimentally all the graphs required are drawn and finished. Experimentally all the graphs required are drawn and finished. So x-intercept will give you threshold frequency. Y-intercept will give you what? X-intercept directly will give you threshold frequency. Y-intercept will give you HF naught. Here it will give you H naught F over E. So I think x-intercept is much more easier to remember. X-intercept will give you threshold frequency. Right now. So don't forget to name the axes. Here hertz, here in joules, here in volt, here in hertz. Right. So there you go. That's how they proved Einstein's graphs and their explanation. Einstein's graph and their explanation. Right. We have a very small wave particle duality also we'll do. It's a very small part. We don't want to increase the workload unnecessary on the next day as well. Good morning, everybody. In a new day, it's Saturday. Right. If you are finished drawing this, tell you are finished drawing. Huh? So that's it. Huh? Einstein's photoelectric effect done and finished. Einstein's photoelectric effect done and finished. The questions you do for homework. I will take a small time tomorrow, and then we'll discuss and finish it. Right? Okay. So I'll summarize it at the very end before we stop. So there you go. So wave particle duality here itself, I'll do it. It's a very simple equation. Now, most of you all know in chemistry, we had who? J.J. Thomson. Tell me what J.J. Thomson did. What did J.J. Thomson do? In chemistry, I learned wave particle duality. Simple concept. J.J. Thomson said electrons are particles. J.J. Thomson said electrons are particles. But his son was also there, George Thomson. J.J. Thomson won the Nobel Prize for saying electrons are particles. His son won the Nobel Prize for telling what? Electrons are waves. So there you have wave particle duality. Understood? Wave particle duality. Okay. So here waves and particles are interconnected. That means they are showing the particle nature as well as wave nature. Now at this moment you can see my particle nature. My particle nature. Do you see my wave nature? No. But there's a wave nature as well. And this particle nature and wave nature are connected by a very simple, interesting equation, which is known as de Broglie's equation or de Broglie's hypothesis. Hypothesis. De Broglie said, if we are a wave, there should be a wavelength. That wavelength is equal to h divided by a momentum. Here, h divided by a momentum. Lambda, it's called de Broglie wavelength. So we have particle, we have a particle, we have a wave. Particle nature is momentum P. Wave nature is lambda. Particle nature, wave nature interconnected. They are coexisting. From this equation, we call it de Broglie's equation or de Broglie's hypothesis. So lambda is called de Broglie wavelength. De Broglie wavelength. H is Planck's constant, 6.6 10 to the power something. P is momentum. So P stands for linear momentum of the object. Linear momentum of the object. H is Planck's constant. Planck's constant. Lambda is de Broglie wavelength. De Broglie wavelength. De Broglie wavelength. That's right. Every particle has a wave nature. Every particle has a wave nature. Every particle has a wave nature. And every wave has a particle nature. Now somebody has said the fellow changed the name and got the Nobel Prize. No, you can't get Nobel Prize like that. You have to prove it. No. Every particle has a wave nature, and every wave has a particle nature, which is called wave particle duality. Which is called wave particle duality. Which is called wave particle duality. Keep writing. From de Broglie's hypothesis, from de Broglie's hypothesis, from de Broglie's hypothesis, we can build a relationship for this wavelength as shown below. We can build a relationship for the wavelength as shown below. We can build a relationship for the wavelength as shown below. Quickly write down. So under de Broglie, of course, this is the only equation that is there. Huh? Right? Okay, done. Finished. So we can keep modifying this. Look at the board now. Lambda de Broglie h over momentum mass into velocity. H over momentum mass into velocity. There you go. Further, we can modify this. But all of us know p squared equal to me. Can you remember this? Mechanics. Momentum squared is 2 times mass into kinetic energy. So momentum is equal to square root 2 times mass into kinetic energy. E is kinetic energy. E is kinetic energy. M is mass of particle. Mass of particle. So I can substitute there for lambda d Broglie, h over square root to me. H over square root to me. There you go. Write down. Momentum squared, p squared equal to me. Lambda d Broglie is h divided by square root to me. Okay. So imagine you are traveling with a particular velocity. If you know the mass and the velocity, you can find your wavelength. Okay. You can find your wavelength. If you know your kinetic energy, you can substitute here and you can get your wavelength, de Broglie wavelength. Okay. Write this example below. Write this example. An electron travels with a kinetic energy of 100 electron volts. A kinetic energy of 100 electron volts. 100 electron volts. Find the de Broglie wavelength. Find the de Broglie wavelength. Find the de Broglie wavelength. So what are they telling you? There is an electron traveling at 100 electron volts. So kinetic energy is given 100 electron volts. 1 electron volt is 1.6 10 to the power minus 19 joules. So 100 electron volt is 100 multiplied by 1.6 10 to the power minus 19 joule. That is going to be 1.6 10 to the power minus 17 joule. So you know the kinetic energy. You know the mass of the electron. What's the mass of the electron? 9.1 10 to the power minus 31 kilograms. 10 to the power minus 31 kilograms. So we can substitute here, no? Lambda d Broglie, Planck constant 6.6 10 to the power minus 34 square root to mass of the electron 9.1 10 to the power minus 31. Kinetic energy 1.6 10 to the power minus 17. Simplify this. You can get your answer 0.12 nanometers. That is your de Broglie wavelength. Substitute. So very simple theory. Yeah? Very simple theory. Very simple theory. So 1 electron volt is 1.6 10 to the power minus 19. Convert to joules. Mass of electron also known. Substitute. Length you can get. Simple example. Okay. So there was more research done on this. Now in light you all learned interference and diffraction. Interference and diffraction, X-rays were sent in and they studied this in detail more. They found out that electrons, when they collide with other electrons, it will bounce off another electron like pool balls knocking on each other. And by that time there are what? Photons emitted, waves emitted, photons are emitted. So all these were studied in detail. So that gives you a very good idea on wave-particle duality. This only is continued for Schrodinger's equation and continues like that. Is it clear? So wave-particle duality tells every wave has a particle nature and every particle has a wave nature. In your syllabus, we just have one practical application. That is the electron microscope. That is the electron microscope. That is the electron microscope. Now remember, once you are doing biology and all, electron microscope is needed. You can see specimens much more clearly than a normal compound microscope. Why? Normal compound microscope, we send light. Electron microscope, we send electrons. These electrons go and knock on particles. When they knock on particles, what? Waves are emitted. These waves we can see, and if we can see those waves, we can much more clearly see the specimen. If you take a normal compound microscope and an electron microscope, what is more clear? Clarity, sharpness, magnification, everything is high in what? Electron microscope. Why? Compound microscope will send in light. Electron microscope sends a beam of electrons. These beam of electrons will collide on what? Travel through a magnetic field. They collide on what you call the specimen particles. And once they collide with particles, what happens? Waves are emitted. These waves we can see. So things we can't see in the compound microscope, we can see using what? Electron microscope, right? In an electron microscope, we use a beam of electrons. We use a beam of electrons Instead of light, we use a beam of electrons instead of light. Instead of light. These electrons will travel and collide with the object. These electrons will travel and collide with the object. And as it collides with the object, the electron will have a kinetic energy. The electrons will have a kinetic energy and also a wavelength. And also a wavelength. And also a wavelength. And also a wavelength. And once we send them through, magnetic lenses, we would be able to obtain a much more clearer image. We would be able to obtain a much more clearer image. Right. So de Broglie wavelength lambda is h divided by square root 2me. Look at this carefully. Here in electric fields, we know kinetic energy is equal to potential difference into charge of electron. Lambda is equal to h 2m, potential difference into charge of electron. Remember, in a electron microscope, when the potential difference increases, delta V is potential difference. When the potential difference increases, the wavelength will further reduce. Normally, our visible range is 400 nanometer to 720. We will be able to see much more clearer wavelengths, much more smaller wavelengths. Okay, no? Much more smaller wavelengths. Huh? That's right. That's right. The electron is accelerated. The electron is accelerated due to a potential difference. Due to a potential difference applied. This electron is accelerated due to a potential difference applied. Due to a potential difference applied. And depending on this potential difference, negative to positive, depending on this potential difference, the de Broglie wavelength will change. De Broglie wavelength will change. And we would be able to see wavelengths which we cannot generally see. We would be able to see wavelengths which we cannot generally see. Now, if you can't see things which you know, now if you look at the sky, the stars you can't properly see. But if you look through a telescope, you can properly see. High resolution. The resolving power is very high. right there. Therefore, under very large potential differences, under very large potential differences, under very large potential differences, the resolving power is also high. The resolving power is also high. Resolving power is also high. Okay. You can draw this. Today we have finished black body radiation, huge section, photoelectric effect, and wave particle duality. Okay, no? Right. Write this down. I'll give a quick summary before we finish off. I'll give a quick summary before we finish off. You all can today night itself before you go to sleep, or now maybe go to sleep. Get up tomorrow early morning and do this MCQs and finish. Huh? Up to page 11, all the MCQs under photoelectric effect. All the MCQs under photoelectric effect. Okay. Wave particle duality will come under X-rays as well. So once you do X-rays, you can do that also. Okay. Do all the MCQs under photoelectric effect. Tomorrow I'll take a maybe very short session and then we'll discuss and finish those before we move on to Sunday. Sunday we have X-rays, small section. Now all small sections are there. X-rays, radioactivity. These are very small. Nuclear reactions is the biggest one. And then very small section, particle physics. Right? So remember in electron microscope, here negative, positive electrons are accelerated under this potential difference. That's your potential difference. So potential difference into charge of electron is your potential kinetic energy. To substitute there, higher the potential difference, smaller the wavelength, greater the resolution. Clear? Greater the resolution. Right. You are finished writing, tell you are finished writing. Huh? Okay. Right. Okay. So, quick reminder from the beginning. So, we have done black body, photoelectric, wave particle duality. So, we have done this completely done. This will do, we have left X-rays, radioactivity, nuclear reactions, and particle physics. This on Sunday we will do. Okay. So these three big topics, these are the biggest topics. These three big topics are done and finished. Right. So black body radiation, we talked about Stefan's law. Stefan's law is for a black body, Q dot equals A sigma T to the power 4. If there is a non-black body, we define something called emissivity. Emissivity times sigma A T to the power 4 will give you the rate of heat emitted from a non-black body. If you take the sun is a black body, sun can radiate energy. The amount of energy coming to a unit area on the surface of the earth is called a solar constant, right? Solar constant. I had to multiply it by the effective area. Effective area of the earth is like a circle. That will be the amount of energy absorbed by the Earth if the Earth is a black body. If the Earth is a non-black body, this should be multiplied by emissivity. Remember, emissivity and absorptivity both are equal for a particular wavelength at a particular temperature, according to Kirchhoff's law. Remember, an object has a temperature T1, surrounding object T2. From the surrounding, we are absorbing radiation while emitting radiation. So the net radiation emitted will be the difference. Absorbed or emitted minus absorbed. Right. Then we have the Boltzmann curves. When temperature increases, the area under the graph will increase. When temperature increases, the wavelength that the maximum radiation is emitted will start to reduce. Clear? And also when the temperature is increasing, for a particular wavelength, radiation energy will also increase. From this, we define Wien's displacement law. The wavelength that the maximum radiation energy is emitted is inversely proportional to the absolute temperature. So lambda mt is constant, k is 2.9 10 to the power minus 3. Also remember this, from here Max Planck said that light is a discrete packets of energy. It's not continuous. It is made up of E is equal to h f. So we discussed all the MCQs. We move into photoelectric effect. When one photon collides with a metal, all the energy is absorbed by electron. Some work is done to come to the surface. That's called work function. If you have excess energy, you will come out with kinetic energy. So actually, the kinetic energy depends on metal to metal. It will change. Sometimes your incident frequency should always be greater than the threshold frequency. So F is larger than F0 means photoelectrons are there. F is equal to F0 or F is less than F0, no photoelectrons are there. Right. And also you can convert this to wavelength and write the relationship like this. Also we drew graphs. Your intensity depends, or your current, photo current depends on the intensity. When intensity is increasing, current will also increase. But for a single metal, the stopping voltage is same. If your incident frequency changes, your stopping voltage also will change. But intensity does not depend on voltage, anything. It depends on the number of photons hitting the metal surface. Number of photons hitting metal increases, current will also increase. Okay, no? Right. Then we move on to wave-particle duality. Wave-particle duality, de Broglie's equation. From de Broglie's equation, h over p, p is square root to me, E is kinetic energy. Kinetic energy we can substitute in terms of potential difference into charge of electron in an electric field. And when the potential difference increases, wavelength reduces, things that we cannot see can be clearly seen. And that is seen in electron microscope. That is why we say electron microscopes have high resolution power. Your homework is all the MCQs under photoelectric effect. Clear, no? Right. Okay then. Thank you for staying patiently. For the ones who stayed from the beginning till the end. Everything, black body radiation, photoelectric effect, wave particle duality, completely done and finished. Yes, we have solved the questions in what you call black body radiation. Do the questions in photoelectric effect, you can see it. Okay, no? Okay then, enough for today. Today, maybe in the afternoon or night, or maybe on Sunday morning or whatever, depending on the time that the Zoom is available, I will put a session to discuss the homework or photoelectric effect questions. So when we do on Sunday night, X-rays, radioactivity, we don't have to discuss that and start. Okay, no? Right. Okay then, enough for today. Catch you all soon. Good morning, everybody.